All right, thank you so much. So yes, my name is Alex, and today I would like to talk to you about how we leverage Rust in WASM-Time. So to start off, what is WASM-Time? WASM-Time is a fast, secure, and lightweight runtime for WebAssembly. But now you might be wondering, what in the world is WebAssembly? So WebAssembly is a safe, portable, low-level code format designed for efficient execution and compact representation. This has been usable in all major web browsers since late 2017 and continues to be widely used today. The main major features of WebAssembly are that it executes code at near native speeds in a sandboxed environment. This specifically makes it suitable for executing untrusted code, basically the same way as how JavaScript is untrusted code in web browsers as well. Despite the name, however, the term web in WebAssembly, it's also designed for out-of-browser use cases as well. So for example, this is where WASM-Time comes in, where we are an out-of-browser runtime for WebAssembly. There's been a lot of growing usage for WebAssembly in this sort of function as a service style use case. So for example, you receive an HTTP request and you execute some WebAssembly as a result. So this takes us back to WASM-Time, where WASM-Time is developed by a consortium of companies in a group called the Bytecode Alliance. This means there's not necessarily one owner or one company that's part of WASM-Time, but it's a whole group of developers in a whole bunch of places. WASM-Time is a standalone engine, so it does not have a JavaScript engine. It is not part of a web browser. It is specifically intended to be embedded in a larger application, used on the CLI, something sort of external from a web browser. Some of the major goals of WASM-Time are to be fast. Users expect WASM to execute at near native speeds, and we must be able to deliver on that. WASM-Time must be secure. The entire development of WASM-Time is very strongly focused around correctness and security, and this is crucial for running untrusted code and upholding the correctness guarantees of WASM-Time itself. WASM-Time strives to be lightweight in the sense of it's highly configurable. You can sort of strip out all the pieces you don't necessarily need and build a custom embedding for just the necessary instructions that you actually want to execute. WASM-Time is highly configurable in the sense that it can run from very, very small devices all the way up to very, very large servers in various configurations, such as with bounds checks, without bounds checks, various sort of trade-offs between virtual memory and physical memory, all that fun stuff. And then finally, one of the major goals of WASM-Time is to be standards compliant. This means that we are active participants in the standardization process for WebAssembly and language ecosystems, and the general properties of trying to make sure that we can all run on WASM in the same way, not just in WASM-Time, but in many other browsers as well. So there's some interesting properties of when you want to write a WASM runtime from scratch, as we were facing when we first started WASM-Time. One of the first things we need is we want it to be reliable. We're running untrusted code. We don't necessarily always know where these WASM functions are coming from. So when we run them, they need to be reliably running as the WASM spec intends without any bugs or crashes. We need to, depending on the actual sort of embedding involved here, a crash or a vulnerability can have a huge and outsized impact, which is further meaning we need to be as reliable as possible. Another aspect is WASM-Time is run all over the place. This is very small devices, many operating systems, all sorts of different places, and in all of these, it needs to be as reliable as possible. No crashes, run the same way, run as expected. At the same time, though, we also need WASM-Time to be very high performance. This is how users expect near-native speeds for WebAssembly, and we need to deliver on that. A lot of this will typically require manipulation of low-level primitives, low-level operating system things, which we need to be able to do from WASM-Time. And then finally, we need WASM-Time to be productive as well. We don't have dozens of maintainers for WASM-Time. We have a small team. We need to be able to make sure that none of these goals are necessarily in contrast with one another. We can't sacrifice reliability for performance, and we also can't sacrifice performance for productivity. So we kind of want everything together. And so we really want this reliability, this performance, and this productivity. And if you've been on the internet recently, turns out there's a fantastic language. You go to wrestling.org and it says you get performance, reliability, and productivity. And so this takes us to my talk, which is how we are using Rust to build WASM-Time for specifically these major features of performance, reliability, and productivity. I'm going to talk here how we're building on top of Rust to get all of these benefits. But then additionally, there's a bit of a missing piece in the foundation here. And so I also want to talk a little bit about Rust's weaknesses. So these are cases where Rust is not helping us or doesn't have necessarily tools. So we're talking about code quality and CI and fuzzing and proving various correctness about the compiler itself in WASM time. So the first thing I want to talk about is the safety and security of Rust. We all know that Rust is by default a safe language, but this really is very important for WASM time in the sense that WASM is used in very high-risk environments. For example, in a web browser, the web browser has access to all the data you have for all your websites, but you don't want to share that necessarily. On a server-side use case, we're running customers right next to one another, and they shouldn't be able to interfere with one another or cause any issues in that regard. An issue here is that Chrome and a couple other web browsers as well have taken a catalog of all security issues that they've encountered. And this blue and this red portion here is 70% of all critical vulnerabilities are memory safety issues. So we're already off to a great start of reducing the amount of critical security issues in WASM time by simply using a safe by default language. The other aspect that has also had some research behind it is that Android, for example, has recently discovered and researched that the amount of new memory unsafe code being written is directly proportional to the amount of vulnerabilities found in a code base. This sort of follows from that sort of 70-30 split earlier, but the idea here is that by writing as little unsafe code as possible in WASM time, we can really benefit the most from the safety and security of Rust. So the general idea is we get to build WASM time by splitting it into safe Rust and unsafe Rust. We can put huge parts of WASM time in the safe Rust category, even if we're dealing with untrusted inputs, such as parsing or validation or compilation. And this goes all the way to the host APIs, for example, the WASI APIs. All of this is 100% safe Rust with no unsafe anywhere internally. We do, however, have unsafe Rust. For example, the runtime and the JIT and the VM. But the nice part about Rust is it helps us encapsulate all of this. So the real power of Rust is not just that we benefit from this, but everyone else can as well. So if you're building a custom host API, if you're building a multi-threaded application with WASM threads all over the place, an async application with lots of WASM Tokyo tasks all at the same time, or a non-standard configuration. In each of these situations, the major power of Rust is that it's not just benefiting us as developers, but it's benefiting you as a user as well. So all of these safety and security aspects extend to our users in addition to us as developers. And we'll kind of see this as a theme through a lot of these benefits of Rust. So the next thing I want to talk about is the performance of Rust. We all know Rust is high performance, but I want to focus on some bits in WASM time. So let's say you have a WebAssembly function and you want to call it. This is one API that we provide in WASM time, but the problem here is it takes this very generic val type. This has a whole bunch of values. It's many different types. It could be quite wide or kind of a very inefficient representation, but it also requires doing dynamic type checks at runtime to make sure you pass the right types of parameters and got the right types of results. So instead, what we can provide in WASM time is a function where we can split these pieces together. So we have a function called typed, where we can say, I'm going to assert that this function has this type at runtime, and you pass in statically this params and results. This gives you a typed func, which you can then call and pass in directly the parameters and results. And so we can specifically separate these halves of type checking and calling, and it's much more efficient to perform the actual call, as we don't have to deal with these extra wide variants or anything like that. So additionally, this is sort of the actual parameters and results here. We can kind of implement it for various traits and types in Rust, such as primitives and floats and all that fun stuff for tuples and many parameters and things like that. We can also extend this to calling functions on the host from WebAssembly. So for example, one way to do this is this new API, but it has the problematic val type that we saw from earlier. This requires type checking of return values, explicitly typing this type, and generally is not very efficient. But using Rust's type system, we can also provide this wrap API, where the idea is we have a single function which has statically enumerated parameters and results, which has similar performance characteristics to calling WebAssembly with a static type signature as well. So this is sort of showing how we can really leverage Rust's type system, Rust generics, Rust monomorphization to provide these very powerful APIs to our end users. So the general idea is that Rust is empowering this ergonomic, high-level, and efficient API design as we as developers of WASM time can give our users. This means that, for example, if you want to call WebAssembly from the host, it can take as little as 20 nanoseconds, which is sort of like a handful of function calls. And to call the host from WebAssembly, this takes even less time, of around 5 nanoseconds or more or less one function call. The other key thing is, like I was saying for the safety and security aspect, this is enabled for all of our embedders, not just us internally in the engine. We have the tools we need in Rust to give you all the APIs necessary to get this performance. Another aspect of performance in Rust is the manipulation of these low-level data structures. So for example, creating a brand new WebAssembly instance in WASM time takes as little as 5 microseconds. And this is powered through lots of virtual memory tricks and kind of bounds checking and all that fun stuff internally in the operating system, which is made possible because we have this very low-level control in Rust. And then finally, we have the ability to share data structures between Rust and JIT compiled code. By having deterministic layout and very fine-grained control of all this memory, we can ensure that both the host and the JIT can manipulate and read these data structures at the same time. So the next aspect is correctness. How Rust is helping WASM time be correct by default, sort of if it compiles, it runs just fine. I want to go back to this type function example. And so the first thing we'll see are these results. This very clearly indicates that, for example, on the left-hand side, this type check can fail. It could actually take an F32 when you said it took an I32. On the right-hand side, this can fail, for example, a trap for a Stack Overflow, for a memory resource exhaustion. So all of this is encapsulated statically in the API signature. Additionally, we can see these parameters threaded throughout the program and threaded throughout these APIs, which basically is showing how we can use this powerful type system not just for the performance aspect, but also for this correct aspect where it's effectively correct by construction. The main thing here is that these vulnerabilities or critical security issues that we're trying to avoid in WASM time are not just memory safety issues. This is that extra 30% of that pie chart that are still found in browsers today, for example. But we'll try to leverage the Rust type system as much as possible to sort of rule these out and make this correct by construction design. A huge part of this is the whole concept of zero-cost abstractions in Rust. For example, there are many, many types of indices in WASM modules, and we have a different type for all these indices, but it's always internally just a 32-bit integer. So this helps us at compile time to ensure we always use the right index in the right place, but at runtime, we don't actually have to worry about any overhead here. As we were just seeing as well, one of the aspects of making Rust sort of correct is the very robust error handling we have. It's very easy to recognize what can fail. It returns a result, it returns an option. It's very easy to handle errors. You can unwrap it. You can use a question mark. You can use a match. And again, this applies to all the users of Rust as well, where when you read code, it's generally quite idiomatic amongst all Rust projects of how errors are handled and how they are very propagated. And so again, just like performance and security, this is all not just for us in WASM time, but also for our developers and users as well. The main thing that we can do is we can focus on providing this high-level, zero-cost API, and you get to focus on your application and not worry about making sure you called WASM time in the right way, make sure you have the right type parameters, and all that fun stuff. Yes. So the next part I want to talk about is portability, the portability story for WASM time itself. This is where WASM itself is a portable instruction format, and users generally expect it to work everywhere. So this could include a variety of architectures, a variety of operating systems, and WASM time needs to run in the same places as well. The great news is that Rust generally seamlessly works on most of these platforms. We as maintainers do not have to be platform experts in each of these platforms to support this. We don't have to understand the installation material, the downloading material, the toolchain material, cross-compilation. All of this stuff is consistent across ecosystems and across architectures in Rust. So for example, how to install a toolchain is primarily RustUp, or a standard Rust toolchain, or via your distribution. Cross-compilation is generally trivial. You pass a -- target flag to cargo, and you're good to go. This is all basically empowering us as developers to very easily take WASM time to all these platforms. Another aspect is Rust crates in general are quite portable. They tend to run everywhere. So for example, Tokyo has an implementation for a wide variety of operating systems. Crates such as Gimli and Surti have a no-stud mode, which means you can practically run anywhere. And so this is another aspect of we can very easily take crates off the shelf and expect them to work basically everywhere. The last part here is that WASM embedders are not always using Rust. And so this portability is not just taking WASM time to different places, but it's also running it in different environments. The great part about Rust is it has an FFI, which is enabled to use through FFI, for example, by not having a garbage collector or not having an extra runtime. And this is what powers WASMtime's C API, our Python, our .NET, and our Go bindings, and C++, for example. And so the last thing I want to talk about that are benefits for Rust is the whole productivity aspect. Again, I was saying earlier that WASMtime does not have dozens of maintainers across a wide variety of companies, but we still need to have all of these very high-quality implementations, this high speed, and all this good stuff. One aspect that Rust really helps us with is that reviewing safe Rust is much easier than reviewing unsafe Rust. We generally make sure that it compiles and it passes tests, and then we just ship it. It's good to go. Unsafe Rust requires you effectively to be an expert in the entire system around it to understand, is this unsafe code actually correct? Additionally, the crate ecosystem makes us much more productive in the sense of we don't have to rewrite all of these things from scratch. Features of WASMtime, such as parallel compilation, are just using Rayon. An ergonomic CLI parser is just using Clap. An optimized runtime for host APIs is all using Tokyo. All of these are high-quality crates in the Rust ecosystem, which let us focus on the WASMtime side of things and the WASM runtime side of things, and not so much these extra fields. And then so again, one of the major aspects here is Rust is empowering not just us, but we ourselves get to empower our users by making them more productive. All of these previous examples of safety, performance, correctness, portability, all help our users themselves focus on their runtime, not the details of WASMtime, and we specifically have all the necessary tools from Rust to guarantee this. So all right, we've got all these great benefits of Rust, but I can see many of you are shaking your heads. I'm just going to assume everyone's shaking your heads. You're all thinking, what about this unsafe code? Then you can't possibly be either safe or correct. You've got that unsafe in there. We've got untrusted third-party code on the crates.io, so you can't possibly be productive. There's no way you can feel more productive in that regard. I don't know, LLVM doesn't have support for my platform, so it's not portable, and CraneLift's got a whole bunch of bugs in it, so it can't possibly be correct. So I'm being a little facetious here, but the real truth is there are weaknesses in Rust that we must overcome in WASMtime. These goals of high performance and high reliability are not simply by using Rust. We still have to go above and beyond to solve issues such as WASMtime has a non-trivial amount of unsafe code. This has real-world implications where we have critical security issues such as problems in our garbage collector or problems of just understanding the unsafe behavior of functions at runtime. The other problem with unsafe is as soon as you have an unsafe block, Rust does not prevent logic bugs, and it means that any logic bug can then become a critical security issue. So for example, we've had leakage between instances in various allocation situations, or we've had problems in the compiler, which allowed guests to have out-of-bounds reads and writes at their own control. Additionally, WASMtime, like any other open source project, is susceptible to supply chain attacks. And then finally, Rust's portability is not always WASMtime's portability. We do have to write platform-specific, Windows-specific, Linux-specific code inside of WASMtime, and so we don't simply get all this for free just by using Rust. So I want to talk now a little bit more about how we actually mitigate these weaknesses. The first thing to talk about is how we mitigate unsafe through improving our code quality, primarily through CI. This is that whole green check mark that everyone wants to see when you send a pull request of all your tests are passing and everything is green. The main thing we do there is we want to run unsafe code in as many ways as possible. This is not just unit tests, but it's also platforms. A lot of times, if one platform has a problem, it's indicative of a problem that could happen on other platforms. It just hasn't been hit yet. Another thing we do is we run all of our code as much as possible through a Rust interpreter called Miri. This performs a whole litany of checks of unsafe code at runtime and is an excellent tool for testing a lot of this unsafe code that we have in WASMtime. It's not perfect because it can't run CraneLift generated code, but it's as good as we can get. As with many other projects, we require that all changes to WASMtime have someone else looking at them, have a reviewer. This is the concept of if you reviewed it and you missed something, or you wrote it and you missed something, the reviewer is unlikely to also miss that at the same time. A great part about Rust is that it makes it super easy to write tests, which makes the project more robust as a whole. So for example, you can put #test anywhere in a crate. You can drop a file anywhere in a folder, and you can write documentation tests and keep them all up to date. This culture of making it super easy to write tests has empirically led WASMtime to have a very high degree of test coverage, and also in the various projects we've seen. The last thing I want to talk about here is the aspect of Clippy. This is an extra tool in the Rust ecosystem which you can go above and beyond the compiler in terms of lints And for example, we have two specific lints that we enable for just a particular module in WASM-Time, which deals with lots of integers. These prevent us from losing data by losing the sign on an integer or truncating various bits. And so in the internals of WASM-Time, these lints are a little too noisy for everywhere else, but we want to be specifically more strict in some internals because we're doing lots of these manipulations. So all of this added together is sort of an example of the tooling that we use to try to ensure this reliability of WASM-Time, not just by using Rust, but also in the development practices we have in WASM-Time. One of my favorite features of WASM-Time, though, is the fuzzing we do. So fuzzing is a primary feature we have for mitigating all the unsafe code in WASM-Time. And if you're not familiar with fuzzing, the high-level idea is you've got this big thing called libfuzzer from LLVM, and it's going to send a bunch of random data over to a program we call in WASM-Time called a fuzzer. WASM-Time will report back, great, I ran that function and it ran just fine. Libfuzzer then mutates this string to something slightly different, and we say, great, I ran that one too, I just ran something different. The goal of the fuzzing process is to keep doing this until you find an input and it causes a panic, causes a crash, causes a seg fault. And so by repeatedly executing a fuzzer with random pieces of data, that's the goal of this whole fuzzing problem. The problem, though, is that we're a WebAssembly runtime, so we probably want to fuzz with WASM modules. And the problem is that if we just take this random data and try to interpret it as a WASM module, we're going to say, great, we ran fine, it's just not a WASM module. And the problem is, as libfuzzer continues to mutate this, we're just going to keep saying, it's great, but it's still not WASM. So we need to go above and beyond this to actually generate some interesting WebAssembly modules. So the goal here is these boxes are little DNA strings, but the idea is that the input can be interpreted not just as data, but DNA for a particular input module. We feed this into a library called WASM-Smith, where the input is a set of decision trees effectively. So it's, for example, to generate a global or a module, or to generate a function or a table, or within a function, whether you want an add instruction or a multiplication instruction. And by using this, we can use this input to generate this module at the very end and have a guaranteed valid module. So then using this technique, we can slice and dice this input. We can say some of it's a module, generating a module to execute along with some exports, but some of it is just some arbitrary data, such as arguments to pass to these exports. We can then execute this WASM module in both WASM-Time and V8, for example, and then assert that the result is the same. This is a technique called differential execution, where we try to make sure that the result executes the same in two engines, and this is a fantastic way to get a very robust amount of testing of not only your entire compilation pipeline, but also the runtime side of things as well. We can take this further, and we can differentially execute WASM-Time against itself. We can use part of the input to generate two different configurations. For example, with and without optimizations, or with and without bounds checks. And by doing this, the WASM should execute differently, but we can test that WASM-Time in very esoteric configurations, which we didn't necessarily test, are all working at runtime as well. And then finally, the last part of fuzzing is we often write very specific one-off fuzzers. This concept of using the input as DNA is not just for WASM modules, but for example, when we developed the garbage collector, we had various operations we want to test, such as generating a GC, getting and setting from tables and globals, various WASM primitives. And the idea is we can, from this list, generate a WASM module, which then does a whole bunch of interesting things specifically related to garbage collection, and then test that, make sure it doesn't leak anything, make sure it doesn't crash, and make sure it passes all of those tests. So the general idea that we've found is if you've got a problem, it's highly effective to throw a bunch of bytes at it, throw a libfuzzer at your problem. One of the main things we do in WASM-Time is we're part of Google's OSS Fuzz project. This gives us over 150 hours per day, every day, of continuous fuzzing. This investment in fuzz-driven development has been absolutely crucial to mitigating issues in WASM-Time and finding them before our end users. This has additionally found regressions over time because we're continuously running fuzzing, and it's found CVEs over time as we've improved our fuzzing and found problems in our existing code as well. All of this is quite easy to integrate into Rust through the arbitrary crate and the cargo fuzz tool, and so generally it's quite easy to drop this into any Rust project, and I would highly encourage you to do so. This is one where I also want to kind of communicate that fuzzing is not just take a look at these bytes and try and parse them, but this concept of using it as DNA of sorts and to generate a very interesting problem, you can write a much more interesting fuzzer, which is not just working on the input bytes. So the next thing that I want to talk about is how we prove CraneLift is correct. This is where CraneLift is WASMTime's compiler, and it will the compilation process is WASMTime will translate WASM to CraneLift, and then CraneLift translate that all to native. The problem here is that if there's a bug in this translation or a bug in the compiler anywhere, the problem can range from just a wrong result or wrong computation to a critical security issue. And the main thing that we have to mitigate against this, because we can't entirely prove that CraneLift is correct, is CraneLift is entirely developed from day one with this idea that correctness is the most important property. As Amani was mentioning earlier in his talk yesterday, it means we're not competing with LLVM. We're not going to implement very tricky optimizations such as loop vectorization or kind of loop unrolling and things like that. These are not going to be in CraneLift, but they could be present in LLVM, for example. Another difference is that CraneLift does not have any undefined behavior in its internal representation. This is in contrast to LLVM, which has a lot of undefined behavior and is often a source of bugs, as the producer and the backend of IR might differ a little bit in terms of who is expecting what from which operation. And then finally, we also have a pretty extensive suite of fuzzers for CraneLift itself, doing differential execution against a reference interpreter and the backends that CraneLift is generating code for. But finally, one of the kind of highest assurance things we've been trying to do is to work with academics in formal verification efforts for CraneLift. So for example, there's a paper about VeriWASM, which is a technique of taking a look at the output of CraneLift and asserting that the properties of the sandbox are maintained in the generated code. More recent efforts have been trying to verify that the lowering rules in CraneLift assert that the semantics of CraneLift itself are matched in the semantics of the actual native instructions that we are selecting and now executing. And so the final thing I want to talk about is how we mitigate supply chain attacks. This is how, in WASMTime, like any other Rust project, we have a non-trivial number of crate dependencies from crates.io. We are just as susceptible as everyone else to a left pad problem or to malware being distributed through crates.io. So in trying to create a high reliability runtime without many security vulnerabilities, this is something that we want to weed out, and we primarily do this with a tool called Cargo Vet. This enables us to review all dependencies coming into WASMTime, both when they're added to review the entire crate, but also when they're updated. So we have a guarantee that every crate update, every crate being used in WASMTime has always been reviewed by a maintainer. And to make this a little easier on us, Cargo Vet enables you to import audits or import vets from other places. So WASMTime will import from both Google and Mozilla, and sort of vice versa as well, or for example, Mozilla imports from WASMTime. So in this way, we're able to sort of share the auditing, share the vetting burden, where we don't have to do literally everything in WASMTime, but only sort of deltas and diffs relative to what everyone else has vetted and verified as well. So that's kind of most of what I want to talk about. I mostly want to highlight that WASMTime has been extremely successful as a result of using Rust, or sort of has been critical to WASMTime's success. Specifically, this performance, this reliability, this productivity has been exactly what we need to be successful in WASMTime and developing a robust and secure runtime. Our safety and correctness in Rust is not only for us as developers of WASMTime, but all of these benefits are compounding for our users. We can empower with API design and the tools that Rust give us for us and everyone else. And then finally, Rust is not a silver bullet. Rust is not solving all of our problems by simply using Rust. And so we have all these extra mitigations in terms of checking CI, checking fuzzing, proving properties of CraneLift. And this is all a crucial story in our correctness and security story for WASMTime. So that's all I have. I'm happy to take questions, but I don't think we're going to do questions. But anyway, thank you.